Following on from our previous video, we started with this formula here, and we wanted to find out what would happen when we vary the distance between the two objects. What would happen when we double the distance, or when we halve the distance here. Okay, so we would start out with this formula here, and we would rearrange it so that we have one bubble here multiplying this bubble here. Well, because we were investigating because we were changing r, we kept this capital M the same, this small m the same. So basically, this is a constant, a constant, a constant. So the whole bubble here is a constant in our scenario, because our scenario we are changing the distance. So it's the distance that changes. Everything else stays the same. So this whole thing here is just a number, and it's a number that we don't really care about. So we just renamed it. So we called it K. So immediately we got rid of this complication here. So it's just K. All right. So now once we're here, well, if someone were to say, oh, F is inversely proportional to the distance, let's just say that it is not in this case. It's r squared. But let's just say this. When you're told this, you could immediately jump to F equals K over R. Well, in this case is pretty much the same. Here K gets multiplied to the top. So we could from here we could say, oh, force is inversely proportional to the square of the distance. Okay, so in our case we do need this square here. Well, anyway, started from here, we got to this stage here, and we found that if you double the distance, you would times you would divide the force. The force would be 4 times weaker. So when you get to this stage here, inside your mind visualize this F, and then you've got the distance here. You've got this kind of a relationship. So when you double the distance, you would actually divide the force will be 4 times weaker. Divide by 4, or you can think of it as 1 over times 1 over 4. So when you are given this here, inside your mind visualize this, and then what that means is if you times the distance by 3, well, this will become times 1 over 9, meaning that you have to divide the force by 9. It's going to be 9 times weaker. So what that means is you see, currently our situation is this: you need to square the distance between the two objects. It's not good enough to say, oh, force is is inversely proportional to the distance. You see, this is not good enough, because if you compare this with this, well, what this means is that if you double the distance, then you would halve the force. You see, it's not halving the force. The force gets 4 times weaker. It's not good enough just to say this. You have to say this, because this is what's happening in real life. So if we compare this here and this, the graph would look like this. Hang on. It would look like this. You see, if you were just to simply say, oh, the force is inversely proportional to the distance, your graph, the purple line here, would look like this. Okay, so this here is the force. So you can imagine the y-axis as being the strength of the force that exists between the two objects, and as you increase r here, the strength becomes weaker. So by you saying that force is inversely proportional to the distance, you see the strength becomes this. But this is what's happening in real life here. The force is inversely proportional to the square of the distance. So that means the force becomes weaker much faster as you increase r. You see, so here you've got to you see that what I'm trying to say is that there's a huge difference between this. F is inversely proportional to the distance, and F is inversely proportional to the square of the distance. You see, this is our situation. You see, this thing here is represented by the purple line. our situation here is represented by the black line, and you can see that the strength becomes a lot weaker, much faster as you increase the distance. So what I'm trying to say is that there's a huge difference between this and and this here. Okay.